This podcast is sponsored by Click Playground. This free programming environment lets you explore and test your data-driven app ideas using Click's engine and APIs. The goal? Less query writing and more efficiency with associative indexing. Visit playground.click.com to learn more and see it for yourself.
Hello and welcome to the InfoQ podcast. My name is Wesley Rice. I'm the chair of the QCon Software Conferences brought to you by InfoQ. InfoQ is a community of software developers who write content that's focused for software developers who lead and drive change and innovation on their teams. Today I'm talking with Jonas Bonér. Jonas is the CTO of LightBend, and he's also the creator of the Akka framework. Today's conversation focuses on Akka and what Jonas calls microsystems. Jonas, welcome to the InfoQ podcast.
Thanks a lot.
I thought we'd start off a bit and talk about Akka. Akka is a JVM-based toolkit designed for developing distributed systems that leverage the actor model, right?
Right.
Can you tell us a bit more about what Akka offers developers?
Yeah, sure. It's essentially two things. I mean, having a reasonably high level and abstraction for working with concurrent applications, as well as working with multiple machines, multiple nodes. And what Akka does is that it unifies these two problems into one single abstraction because it sort of makes distribution first class. So it really doesn't matter if you scale out, so to speak, on multi-core, building concurrent and parallel applications, or you scale out on multiple nodes, sort of building distributed applications. It's the same programming model. And I think that's one of the beauties of actors in general, that they make the network and distribution first class, which also happens to work very well for scaling sort of up, on multi-core architectures as well.
Okay, so let's talk about the actor model for just a second. The actor model is an approach for writing concurrent systems that treat kind of actors as universal primitives. The idea is actors can only modify their own private state, and they pass messages to each other, thus avoiding locks. So what was the goal for Akka? Was it just to create an implementation of the actor model, or was it something else?
Yeah, the core actor model is extremely simple. I mean, it's a general model of computation that was created by Carl Hewitt in the early 70s, and then was sort of popularized reasonably, at least, by Joe Armstrong and Robert Verding's Erlang, and it's getting sort of a new wave. It was created in the 80s, but the last sort of 10 years it's been popularized in certain groups. But it's still sort of an obscure language to some extent, in Prolog, derivative, and stuff. So the reason for creating Akka was essentially I wanted to get these great ideas onto a platform that most people use, and I chose the JVM to do that then.
So can you give me like a really solid use case so developers can get their mind, senior developers can get their mind around when Akka and the actor model is the perfect choice?
Yeah, sure. It's Akka is both low level and high level. You can say it's really high level for being a fabric, a distributed computing fabric, because it abstracts the sort of away a lot of the hard things by making sort of say the network first class and a lot of the hard things with distribution in general, partial failures and drop messages, etc. All that is first class, which means that you have the tools to actually build truly reliable systems, and the abstractions are not getting in the way like they are often have done in the past. RPC or EGBs and stuff, XA transactions. They try to do too much in terms of abstractions over distributed computing and distribution in general, and by doing so they leak and they make it really hard to make it work when things don't work, essentially. But actors make that reasonably easy. That said, it's not the ideal end-user programming model to build any kind of applications. And that's the reason why we have added sort of layers on top of the core actor model, like, for example, Akka Streams, which makes it very easy to do workflow across actors and sort of fanning in, fanning out, doing some transformations on the way, etc. And we've also experienced with other sort of abstractions, like software transactional memory or in the early days, etc., which we faded out or dropped support for because it didn't work that well. We also had sort of closure style agents, and so we've sort of been toying with a lot of different abstractions. But the fundamentals have always been the actor model. And I think the most successful abstraction on top of that have been streaming now, because as you know, I mean, the world is going streaming, and streaming is a very hot topic now for a lot of reasons. I mean, it's also a lot of good, interesting problems, and I think Akka streams provide that, on top of actors in a nice fashion.
I want to talk a bit more about Akka streams in just a second, particularly because it's an implementation of reactive streams. But first, I'd like to stick with the fabric concept. So does Akka build in patterns like circuit breakers and bulkheads? Well, obviously there's bulkheads because it's very nature, but does it build in these common patterns that we're starting to expect with distributed systems into the actual fabric itself? So you're kind of like starting with kind of these best practices of distributed systems?
We have circuit breakers in Akka, and we've had it, I mean, almost since the beginning, 6-7 years ago. And I think that's a key part of it. I think as you said, bulkheading is the foundation. I mean, isolation is essentially to allow an instance to die in isolation and be restarted in isolation. But circuit breakers can also be very important to protect the instance, before it dies. If you communicate with another service that is sort of unreliable, then circuit breakers can be a very nice tool to sort of wrap that unreliable communication channel in a circuit breaker to simply protect yourself. That if things go haywire and and it's sort of out of your control, right? Because it can be a third-party system, then it sort of will not affect you more than you allow it to. But the circuit breakers sort of capture that failure, and you have some sort of backup and retry policy.
I was going to ask about retry. Yeah. So how does that whole system work? Is like I remember talking to Adrian Cockcroft, and he was talking about retry policies and basically how the closer you are to the user, the longer the retry should be. How does Akka or a fabric like Akka manage the retry cycles throughout service request of the entire system?
That's an excellent question. Unfortunately, we don't have any tools that helps you with that, and I don't think I haven't seen any ones that really does that.
Okay.
But it's a very much a real problem because when you start having multiple circuit breakers with different backup policies, or different timeouts. This also applies with just timeouts, and you start composing them. I mean, you need to know what you're doing really, because it can be like the top client when you compose all these and things, and you're unlucky with their timings. I mean, it can be he might have to wait 30 minutes, right, for all of these to functionality to be fully restored. So absolutely, I wish there was, but in order to do that, I think you need to sort of zoom out and have sort of rely on sort of visibility tools, right? Transparency tools like monitoring and these type of things that takes a system view on things, that allows you to view how components interact and how they integrate and follow flows, all the way from A to B and across your whole system. And we are working on that at LightBend, and we're working with partners like OpsClarity that does a good job of doing that, for example. But we as an industry have extremely immature tools in general to understand how distributed systems work at large. Really the systems part, not the individual components. So I think we need to go back to the drawing board to some extent there.
You mentioned earlier that Akka takes its inspiration from Erlang, and Erlang takes its inspiration from a paper back in the early 70s written by Carl Hewitt that kind of just defined this actor model that we were just talking about. But there's something that I find really interesting in all this, and it's actually something that's come up in our committee calls for KubeCon London. Martin Thompson's brought it up, and we will actually have a keynote in March at KubeCon London that kind of focuses on the subject. But in the early 70s, there was a ton of research around distributed systems. And then it seems like we kind of moved and focused mostly on concurrency. And now we've kind of circled back, and we're back kind of revisiting this research of the 70s on distributed systems. So is this just a function of Moore's law playing out in that we're having now to move to many cores, or is there something more fundamental that's happening for us, kind of returning back to this original work?
Yeah, I think it's essentially two different trends, and the first one is that trends when it comes to hardware and environments, and that is the first is a move towards multi-core, and that is of course driven by Moore's law. And that is I mean, essentially all processors nowadays are more multi-cores, even the phones and whatever you almost deploy on now. But the other move is also the move to virtualized environment and cloud and essentially back to utility computing where you sort of pay as you go. And to do that, you need sort of platforms that can take advantage of that can sort of scale on demand, scale up when the load goes up and scale down. I mean, equally fast when the load goes down to save sort of energy, to save cost, etc. And I think to do that, of course, you need to embrace distributed systems. But you also have some other sort of drivers, and that is that users today are extremely picky when it comes to reliability, for example. That systems simply cannot fail today. And as we all know, I mean, it's impossible to build a fully resilient system using a single node, because if that fails, you're screwed. So you need at least two, and if you have two nodes, then you have a distributed system. So then the question is, how do you manage that? How do you manage state? Is an active passive sort of model using sort of SQL or SQL database replication under the hood, or do you need some more sort of real time type of approach of data replication, or do you try to go stateless? All these problems sort of arises, and often two nodes is not sufficient either, because the other thing is that you need to, as I said, over the scale, and then you need to sort of being able to add nodes on the fly while the application is running. So I think these drivers are what sort of brings us back to the fundamentals essentially of distributed systems. I mean, the ones we took at the CS class back in school.
Yep.
They're all something that we need to practice today. It's not just not just theory anymore.
Right. So you talked about reliability and resiliency, which immediately triggers the Reactive Manifesto to me.
Right.
First off, can you just recap Reactive Manifesto and kind of the goals behind getting together and expressing the Reactive Manifesto?
The React Manifesto didn't come up with anything new, really, to be honest. I mean, it's sort of tried to capture a lot of the good ideas that's been out there, and all the way up back to the 70s with Carl Hewitt, and the work of Pat Helland and Jim Gray on tandem systems, and Joe Armstrong's work, etc. But also a lot of the sort of the trends that we've seen the last years, people picking these ideas up in different communities, often using different sort of names for things and different sort of ways of talking about it. So I saw the need sort of to try to unify these into a simple framework to make it more approachable for the general developer, not just the die-hard hackers that sort of live and breathe distributed systems every day, at night after work. And so it was the first goal was sort of try to capture it in a simple framework, simple way of explaining it, and also come up with a vocabulary to talk about it in order to sort of bridge communities. So we have one way across, .NET, Java, Scala, even Go and JavaScript communities to talk about things and sort of communicate essentially. And as you've already sort of hinted at, I mean, it's essentially a framework or a set of principles in order how to build reliable and systems that scale. So the two different sort of forms, you can say, I mean, is that it should be elastic and it should be scalable and it should be resilient. And that, if it sort of can react to failure in a sort of graceful manner, either through graceful degradation, but even more being truly resilient and self-heal, coming back from failure, as well as sort of react to unpredictable load in a graceful way, adding new resources on the fly, and as also shrinking whenever needed. Then the system can always be responsive. I mean, not just in the happy path when things go, as expected, which they never do in distributed systems. I mean, eventually reality will come and hit you, right? And then you need to have sort of principles that support the application in order to be elastic and resilient, even when things aren't going as they are expected. We really believe, we that wrote the manifesto, that one of the core principles that allows that is to fully embrace asynchronous message passing, because it gives you the decoupling that is essential for things like isolation to be truly resilient, to add things like supervision, to be able to sort of understand that a process has gone wrong from a healthy context, and being able to manage that without you being tied, in space or in time to that component, meaning that you will be affected by that is going down, and that leads to cascading failures that we often see in enterprise applications, etc. And why it's important when it comes to elastic systems is essentially that it gives you what we call location transparency. And location transparency means that you have mobility, that the system or the users of the system or the individual components that are using other components don't care or doesn't have to care where the components is currently running. I mean, where it's actually, how essentially the topology of the application or the system, and because that's something that can change while the application is running, and that's also sort of gives you what you need to really sort of take advantage of the promise of cloud computing, scale on demand, etc.
One of the things you said is it establishes a vocabulary to talk about systems that are reactive. One of the things that jumps out at me is the usage or the use of message-driven as opposed to like event-driven.
Yeah.
Can you discuss the difference between the two and what that means?
Sure. Event-driven is generally about publishing facts,
right,
to anonymous sort of listeners. I mean, it can be 0 that currently listening when you publish the event, or it can be 10, 50, 100. You don't care. I mean, you are publishing an event to whoever have subscribed, and that process or that mechanism is usually local, and there are different sort of DSLs or programming models that you can layer on top of that. One is callbacks, for example, that we've seen with the Node.js model or the reactor style model and so on. And another one is for example, using combinators, more functional approach for transforming the events as they are pushed downstream. And that's a very useful and very simple sort of paradigm to understand. But the problem with it is that you can't model communication on it because you're not working with addressable recipients like you are with message passing. So message passing is all about sort of abstracting over communication with the process A talks to process B and sends a message directly to him, to that address, so to speak. Right. So message passing, on the other hand, is a great tool to model distributed communication. And I think that's why it's the foundation for reactive systems, while event-driven is the foundation for what a lot of people call reactive programming. And reactive programming tends to be great within the individual components. You get better performance, making more responsive, asynchronous and non-blocking execution, and these type of things. And it's also great for working with streams. But it's not a great model to model the sort of distribution on. So often you need to pair these two. So you have often a sort of an event-driven model as the model that you expose to the end user, while message-driven is the way the things work under the hood to transfer and things over the network and making all the plumbing work.
You just hit on something that I thought we might talk about too, and it's that if there was an award given for the most overloaded term of 2016, it would probably be the word reactive. We've got, we talk about Reactive Manifesto, we talked about reactive streams, we talked about, you just mentioned reactive styles of programming.
Yeah.
Can you talk a bit about all that? So we obviously just talked about Reactive Manifesto, so architectural style of making resilient, responsive systems that are message-driven, that are elastic. That's the Reactive Manifesto. Yeah. But what's reactive streams, and then what is the reactive style of programming.
Sure, I totally agree. I mean, it's an extremely overloaded term, and it means different things to different people, and that's not necessarily a bad thing. I also think that terms need to evolve, and in order to sort of stay relevant, and the manifesto has evolved, and the thinking there, and I'm really happy that others pick reactive up, right, and pushing the ideas forward. So to clear things up, Victor Klang and I wrote an article for O'Reilly on reactive programming versus reactive systems. And reactive systems is what we talk about in the Reactive Manifesto. That takes sort of a big systems approach to things, how multiple components interact in terms of being elastic and resilient and always responsive. But reactive programming is sort of this other trend that actually has roots also way back, in the 80s and at least early 90s. I've already said that's event driven. That's great for within the local component or at the edge of the component. It's not about building systems, but making individual components really efficient and making the maximum use of the hardware, etc., through non-blocking execution and asynchronous sort of execution. I don't know if we should talk more about that, but reactive streams, as you mentioned, that's essentially that was sort of a joint effort between us at LightBend and some other firms like Pivotal, Red Hat, Oracle, Netflix. It's essentially a simple standard for doing streaming with back pressure. So the important thing here is the reliability that back pressure gives you, that the producer can't overload a consumer and therefore take him down because you hand him too much work that he can't deal with. So the consumer can flag that, sorry, I can't take any more work than this, and then the producer slows down. And the important thing with this specification is that in order for this to work, every single sort of stage in the data flow sort of pipeline needs to participate. And often you use quite a lot of different tools in an application. It's usually not just one tool or one framework or library that you're using. This sort of simple specification gives the implementers of these tools a way to write, their SPI in a way that it can be hooked together. So back pressure is propagated all the way up to the client at the top, and all the way down, wherever the data stream ends up.
Okay, so we've talked a bit about Akka, the Reactive Manifesto, overloading of terms like reactive. I'd like to shift just a bit and talk about your KubeCon London talk. The title has evolved just a bit, right? It was from Microservices to Microsystems, and now it's microliths to Microsystems. Can you talk a bit about what you're trying to communicate with the title and your goals and hopes for this talk?
Yeah, sure. So the title is essentially that means, that thinking simplistic and not going all in on what it means to build microservices and systems of microservices. Then you will just shoot yourself in the foot, and you will just get all the drawbacks from microservices, because it's all trade-offs. Microservices is not a silver bullet in any way. It adds a lot of complexity.
Right.
It has quite a lot of baggage. But if you do it right, then you can reap the benefits, and then it's absolutely can overweigh the drawbacks. It's extremely contextual. I mean, you need to sit down and look at, what kind of application are we building? How big is our teams? Will it sort of pay off to split up, into different teams, and having each team, deliver services or ship independently, etc. Or is it easier that we just ignore this and either build a monolith, right? But I wouldn't suggest that, but perhaps just build a distributed monolith. That's sort of an anti-pattern. It's been sort of talked about as an anti-pattern, but that's essentially how we built systems in Akka all the way. You get resilience, you get sort of elasticity, but you don't have to pay the price of having to sort of split up in, for instance, protocols and like you do with microservices, because you don't need it. On the other hand, if you have a large organization, then it can be absolutely critical that you do split up.
What about the use of the term microsystems? It's pretty intentional.
What I mean by that is that essentially, creating a single instance of the microservice, there's a lot of good sort of scaffolding frameworks that allows you to create an executable jar, that you just run up and to run a single instance of a microservice. But that doesn't do any good at all. I think because every single microservice that I view, it needs to be viewed as a system. It needs to have sort of multiple parts that usually run on different machines in order to fully function and be resilient. And often it allows to sort of split up the stateless part from the stateful part, and have the stateful part, being sort of active, passive, perhaps, and then the stateless part scaled out independently of the stateful part. That's one, and often it forces you to rethink how you do persistence, for example, embrace either NoSQL databases that also forces you to go distributed, or embrace things like CQRS and event logging that also pushes you down that route. And on top of that, you have everything like service discovery and service gateways that you communicate with, et cetera, et cetera. So, and I think thinking holistically, that embracing the fact that creating one single microservice still means that you need to build a distributed system. That is what I mean by microsystems.
I remember there was a pretty famous blog post from a few years back that Martin Fowler was talking about kind of things that you had to have in place to do microservices, to do them right. It was called "You Must Be This Tall," or it referenced "You Must Be This Tall." And it had things in it like rapid provisioning, basic monitoring, rapid deployment, and a DevOps culture. So I wanted to ask you, what are the things that are kind of like you've got to get right before you start trying to deploy a distributed system in your enterprise?
It's a very good question. Of course, it goes all the way back to people and process and their knowledge, of course, and splitting it up into teams like a microservice can help there. Sort of the soft side of microservices and the process side of microservices. But I also think that what a lot of people are forgetting when they jump straight into microservices is the fact that they are about to build a distributed system. So I think in that, I think going back to first principles and think about what it really means, and reach for tools that allows you to the abstraction to scale as the application grows, scale in terms of understanding and simplicity, as you have sort of accidental complexity under control and or minimizing that. And I think I've learned the hard way that embracing reality, and the constraints helps a lot here instead of trying to sort of fake them and hide them and pretend that they are not there. That's why I like the actor model. That's why I like sort of going all in on distributed systems in terms of messaging, etc. That's extremely important because that lays the foundation for you to succeed instead of trying to going from a monolith to microservices architecture. Just making every single method dispatch a REST call, for example, etc. That introduces too strong coupling instead of taking the advantage of really loosen up the coupling and decoupling things as much as possible to allow them to evolve independently and et cetera, et cetera. I think that's really key. But you've also touched on some of the other sides that comes after development. That when rolling things out, continuous delivery is extremely important, and now allow to roll both forward and back. If things go wrong. Things like blue-green deployments and canary deployments and stuff like that. There's a lot of good things written there from Netflix, for example, as Adrian Cockcroft talks about it, etc. But also, like we touched, under having sort of tools that understand the system at large. There's also the visibility part and having transparency into what's really going on. Log everything. That's at least the basics, but often you need more than that. You need to ideally understand the flows and how components interact with each other, etc. And we're not really there as an industry, but there are starting to emerge some good tools, I believe. to capture that. We're working a lot at LightBend now with using machine learning to try to understand what's going wrong in the system, anomaly detection, predictive scaling, and these type of things. And I have high hopes for that. Machine learning and AI will help automate a lot of this. And there's a lot of sort of talk now about serverless, and we can have a whole show on that, I guess. But for me, that's all about trying to remove the operations from the picture. So more ops-less than serverless. Having the cloud infrastructure automate as much as possible. And I think AWS Lambda is just the first start. It's more of a stateless model, function as a service, etc. I think there's a need for embracing, and moving forward on taking the serverless mentality, the ops-less, operationless mentality further, but for building real systems. I mean, systems that are, stateful, and as everyone's built distributed systems, state is where the hard things happen and hard things are. But there's a lot of things to be excited about because the things are moving rapidly in the industry.
Yeah, we could definitely do a whole show just talking about serverless and kind of its implications. In some ways, though, it's still a similar story. Like, how do you trace and how do you log successfully in a serverless environment? It's some of the things that we're solving with microservices today. So there's definitely some overlap and interesting things there to discuss.
Absolutely.
So you just mentioned something that I wanted to kind of catch on because I hadn't heard anything about it. You mentioned that you're working with machine learning and AI at LightBend to kind of help understand, I guess, like paths or tracing through distributed systems and architectures. Is that what I heard?
Yeah, we have a new product that we're working on that's out in alpha right now. So it's very early days. We call it the Fast Data Platform, and it's essentially a platform for doing streaming and simplify the complex landscape of streaming. I mean, streams is an extremely overloaded term as well. Yeah. And you have Akka streams, you have distributed streaming, you have like Spark streaming, more big data type of things, and some things are real time, some things are more batch oriented, and you have things like Kafka in the middle. And how do you make sense of all this? And that's essentially what we're trying to simplify. But we're also working on adding sort of components and layers on top of that. And some things like that are, for example, anomaly detection and predictive scaling, predictive maintenance, and things like that. And we have plans sort of to feed that, to not just expose that to the users for their application, which is of course the first priority, but also to feed that back and have that work on the data that we collect from running this in the cloud for the user, and then sort of allow that to influence the actions in terms of scaling, in terms of resilience, etc.
So it's a cloud offering that basically can give you some insight into how you're executing your code.
Yeah, and do that in as much an automated fashion as possible. So sort of taking serverless to the next step, I'd say.
Okay.
But it's early days, so.
Sure. Very cool. All right, so I wanted to ask you one more thing, and then I'll kind of wrap this up. But I like to try to kind of elicit patterns that you see that are useful for developers to kind of focus on. And one of the ones that I've heard you talk about is kind of the saga pattern. Can you, which is kind of a way of managing long-running transactions in a distributed system.
Yeah.
Can you explain kind of how that works and how a developer might be able to leverage a saga pattern with something like Akka?
Yeah, absolutely. I mean, it's actually a quite popular pattern.
Yeah.
As I said already, I mean, but both for regular distributed systems, it's been used in Akka for quite some time, but even more now when it comes to microservices, right. and it fits very, very well with sort of messaging style architectures and so on. And it's essentially the idea instead of using distributed transactions, XA transactions, where essentially you have a global lock, and then and everyone need to say yes, and then you roll back everything or not. you base it essentially on the protocol of guessing, apologizing if you were wrong with your guess, and then performing a compensating action if you were wrong. So it's a more loose way of thinking about the world, that it's okay to take an educated guess, it's okay to be wrong, and it's okay to then sort of just apologize and perform some compensation. That's very much how the world works. Yeah. With ATM machines allow you to withdraw money even though if they can't reach the mainframe, and then once it's restored, the connection is restored. I mean, it deducts it from your bank account, or how we see airplanes sort of overbook airplanes, and then sort of try to bribe themselves out of the problem by issuing vouchers, etc. Hopefully some will get it. And the Saga pattern sort of is a framework for that. It sort of gives you a way to split up the workflow, into multiple sort of transactional steps. So the overall consistency can be achieved by grouping all these transactional steps. But what was interesting that each step is sort of has an action, do X, right? But it also has a compensating action, reverse X. So then you execute that in sort of an eventually consistent fashion, like step by step by step. By performing the operation, and if one of them goes wrong down the line, all this can happen asynchronously. Then the reversing transaction is applied in the reverse order for each one of these steps. They can live on different nodes, and everything happens in a fully asynchronous fashion. So it's really about trying to take a bet that each part of the transaction will hold, and if it doesn't, you just roll it back by issuing compensating actions.
So it sounds a lot, it reminds me of like the command pattern with undo, right? You issue an action, and then you have the ability to undo that. Is that pretty accurate?
Yeah, absolutely. It's a very simple model, and it works really well, but it forces you, of course, to loosen up on the consistency demand requirements that you have, and model the data integrity within these components in a different way than you would do if you have one single schema and sort of ACID in terms of relational database, etc. Which of course forces you to have transactions, right? But so it all goes back how you model the data and how you think about the world, essentially. But the interesting thing that in my experience, that this way of thinking matches reality quite well. It's just that we as developers are used to thinking in a simplified world, where everything is atomic, where we have one single present, we have control over the whole world at the same time, right? That's not how reality works. You have multiple things happening concurrently all the time, and we live very much by compensating actions, I believe. So once again, embrace the constraints. It can be liberating.
Yeah. I like it because it forces you to focus on not only the success path, but what's the failure path and how to get back to a normal state. I like that a lot.
Exactly.
So we've been talking with Jonas Bonér, the CTO of LightBend and creator of the Akka framework. Jonas will be speaking at KubeCon London on microservices and their reality. So if you're in Europe, be sure to stop by and catch his talk. Jonas, it was truly a pleasure to chat with you, sir.
Thanks a lot.